Hello, awesome students.
Hi, I'm Avik. I will be your instructor for this course. Let's first understand what is an electric charge or simply charge. So, electric charge is the property of subatomic particles that causes it to experience a force when placed in an electromagnetic field. There are two types of electric charges present, positive and negative charges, which are commonly carried by charge carriers, protons and electrons. The unit of electric charge is called coulomb, named after the French physicist Charles-Augustin de Coulomb, who formulated the famous Coulomb's law. Now, let's understand mathematically how a charge is defined. Mathematically, a charge, Q, is defined as the product of electric current and time. So, Q equals I into T, where Q is the electric charge, I is the electric current, and T is the time. Next, we move on to the concept of a field. In terms of physics, a region in which each point is affected by a force is known as a field. For example, we can think of any object that falls from a height to the ground. Ever wondered why? This is because everything on our planet Earth is affected by the force of gravity. Hence, we are all under the influence of the Earth's gravitational field. Now, we know what a field is. So, let's dive into the concept of electric field. An electric field can be considered as an electric property associated with each point in the space where a charge is present in any form. In other words, an electric field is also described as the electric force per unit charge. Now that we understand the concepts of an electric charge and an electric field, let's understand what happens when a charge starts to move. As we discussed earlier, an electric charge is associated with an electric field. And the moving electric charge generates a magnetic field. Hence, the combination of electric and magnetic fields is known as the electromagnetic field. No force is experienced by a charge that is not moving. So, when a motionless charged particle exists in a magnetic field, it does not experience any magnetic force. However, as soon as the charged particle starts moving within a magnetic field, it experiences an induced magnetic force that displaces the particle from its original path. Here, in this diagram, Q is the electric charge, and V is the velocity with which the charge should move linearly. But, due to the presence of magnetic force, V, it experiences an induced magnetic force and deviates from the original path as shown. This phenomenon, known as the Lorentz force, is consistent with the rule that states magnetic fields do no work. We'll discuss Lorentz force later in this lesson. So, mathematically, the equation that is used to determine the magnitude of the magnetic force acting on a charged particle, Q, moving a magnetic field, B, with a velocity of V at an angle of theta is F equals Q, V, B, sine theta. Now, let's look at what is the force that is due to the electric field. The force due to the electric field on a charge, as discussed earlier, is built into its definition. The force always acts either parallel or anti-parallel to the electric field and is independent of the velocity of the charge present. In other words, this force has the ability to do work and impart energy to the charge. Mathematically, it's represented as F equals Q and V. Next, we need to understand what is the force that is associated due to the magnetic field. As discussed, magnetic fields can exert a force only if the charge is moving. Also, the magnetic force always acts perpendicular to the velocity of the charge. Mathematically, it's represented by F equals Q V into V, where F is the force, Q is the charge, V is the velocity, and B is the magnetic field. Now, let's conclude on what is actually the Lorentz force. By definition, the force exerted on a charged particle, Q, moving with velocity, V, through an electric field, E, and magnetic field, B, is known as the Lorentz force. The entire electromagnetic force, F, on the charged particle, called the Lorentz force, is given by F equals Q into E, plus Q, V, into B. Here, the first term is contributed by the electric field. Second term is the magnetic force and has a direction perpendicular to both the velocity and the magnetic field. Now, as we understand the basic concepts, let's dive into a numerical. An electron moving perpendicular to a uniform magnetic field 0.500 Tesla undergoes circular motion of radius 2.8 millimeters. Find out what is the speed of electron. Charge of an electron, Q equals minus 1.60 times 10 to the power minus 19 Coulomb. Magnitude of magnetic field, B equals 0.500 Tesla. Mass of the electron, M equals 9.11 times 10 to the power minus 31 kilogram. Radius of the orbit, R equals 2.50 millimeters equals 2.50 times 10 to the power minus 3 meters. So the velocity can be found by using the formula V equals Q multiplied by R, B slash M. Hence, after using simple calculations, we get the value of velocity V to be 2.195 into 108 meter per second. Looking forward to an awesome lesson with you guys again. Thank you for watching the video. If you have any queries, drop them in the comments section. Please visit our website lambdageeks.com for more articles on technology, engineering, mathematics, and various other domains. You can check our other website as well. We have features like YouTube Trends, Twitter Trends, Scientific Calculator, and many more other tools. If you like our video, please like, comment, and share. If you have any questions, please comment and we will resolve your query.